Today I'm going to show you how to prepare the protein for molecular docking analysis. This is a series of videos, as I have mentioned earlier, that I'm going to show you what are the softwares required and how you can prepare proteins, ligands, and how to represent it schematically. So all the aspects of bioinformatics analysis on molecular modeling and drug designing aspect will be shown here. So the first thing what we need is the installation of the MGL tools. I hope you guys have installed MGL tools. As I mentioned in my previous video, that you can navigate to the site of Scripps Research Institute, and then you can download the MGL tools. And one more thing to remember is that MGL tools only works with Mac OS Catalina. It won't work with Big Sur or the latest version of the Mac OS, but it works with Windows and Linux perfectly. So the Windows users and the Linux users, you don't have to worry about installation of MGL tools. But for the Mac OS users, you need to have Catalina, the operating system version on your Mac, so that you will be able to run MGL tools. But no worries. And in my previous video, I have also mentioned how to use the parallel in which you can utilize a Windows operating system on your Mac, which is a commercial software. I hope you guys have purchased this version of the parallel, the 17. I think parallel 17 version is available for macOS Big Sur, and you can access Windows operating system inside the Mac, and you can install MGL tools and Discovery Studio Visualizer and many other software which are supported by Windows. So coming back to the molecular docking approach, so today we'll cover the protein preparation, and in the subsequent videos I'll be presenting you the ligand preparation as well, and later on I'll show how to dock the chemical compounds or the ligands to the protein using AutoDock Vina and AutoDock 4.0 as well. So basically, this structure-based drug designing, plays an important role in drug discovery and complements other virtual screening approaches. So in general, the first thing what you need is a protein. In general, these protein crystal structures are prepared prior to the docking, and we do a lot of structural modifications by adding hydrogen atoms, optimizing the hydrogen bonds, remove the atomic clashes, and perform other operations that are not part of the X-ray crystal structure refinement process. So basically what we do generally is if we navigate to any of the papers, if you open any publication, scientific publication, there you find different types of protein targets and their inhibitors. So in this case, if you go to this particular publication, they have mentioned that they have used MPRO as the protein target, and I think PF 07321332, which is a drug. I think the name is Nirmatrelvir. So this drug they have docked with the MPRO inhibitor. You can see if you scroll down below, you will see how they have docked the structure to the MPRO target. So we need the MPRO protein structure from PDB database, which the MPRO PDB data MPRO from the PDB database, the ID is 6LU7. This is a very popular protein, protein target. During the pandemic, this particular protein structure has been used widely. So go ahead to the PDB database and enter the ID 6LU7 over here, 6LU7, and you go here and download the PDF format. So if you download the PDF format, there you go, you have the PDF format. And regarding the ligand preparation, I will deal with this in my next video, in which how to prepare the ligand. And so today we'll be focusing only on the protein structure preparation and what are the things that are required to modify the protein structure, because this is derived from X-ray crystallography. Yes, X-ray diffraction. There might be some missing bonds or missing hydrogens, and a lot of other structural modifications that we need to do prior to the molecular docking. So let's get started. So since you have downloaded the 6LU7 from the PDB database, what you can do is you can open with Chimera. As I mentioned earlier in my previous video, that you can install all the softwares that are required. One is Chimera. You can use Chimera X as well. So I'm going to deal with the protein by using Chimera. So if you open Chimera and the protein structure, you will see the ribbon structure of the 6LU7 protein, MPRO of COVID-19. So this is the default settings. You can change it later on. You can put the black background or maybe the white background, but I prefer the gradient background over here in Chimera, which looks much more vivid. And so when you open any protein structure, it only shows the ribbon form. But if you go here, action and atoms and bonds, and if you click on show, it will show all the side chain residues, the ball and stick model, and what are the all the non-standard residues as well. So if you go here to the residue section, you will see there are some non-standard residues. So if you click here, these are some of the non-standard residues. I think this is the inhibitor that has been proposed in the PDB database during the X-ray crystallography diffraction experiment. They optimized I think the protein along with the ligand, that is called N3. So before going to the docking module, I would suggest everyone to delete all the non-standard residues first. So if you go ahead, if you go over here, action, atoms and bonds, and if you go here, there's a delete option, so you delete. So now if you go over to select and residue, you won't find any non-standard residues. And one more thing is that this particular protein, it contains two chains. One is A and another one is C. So if you click C over here, and if you want to zoom in to see what the structure looks like, go here, action, and then go to focus. So if you focus, then it is highlighted in green color like this. You will see this is the C chain. So you don't need this, you just need the pure protein, that is the A chain. So go here, action, atoms and bonds, and delete. So the C chain has been deleted. So go to here, select, clear selection, and go to action, and again focus. So you will get the original structure. So if you want to prepare the protein for the docking approach, you have to go to the tools, structure editing, and dock prep. So this is the dock prep tool, and make it default. If you want to delve into the properties, what are there in this particular dock prep tool section, you can read the documentation of Chimera, but here I'm using the default options. So click OK, and here it is the protonation state for all these particular residues. So generally when you download any structure from X-ray crystallography, so the protonation states of histidine are bit distorted, I would say. So this is the tool which can help you to retain the charges, correct the bond orders, and make different types of structural modifications prior to the docking. So go ahead and click OK. And here, if you have non-standard residues, you don't require any non-standard residues that are chemical compounds or any other chain. So if you have those non-standard residues, then you can add castigate charges. Otherwise, amber force field has been used for the standard residues. Those are the particular amino acids. So if you want to add labels and the charges to the atoms, you can add labels to that, but go ahead and click OK. So it will be saved as a mol2 file. As you can see here, this is the mol2 file. So I'm going to save it as 6lu7 modified. Okay, and click OK. So the mol2 file has been saved, and you can see, if you zoom in, you can see there are different charges associated with this, and you can see these white color sticks. These are nothing but the hydrogens, because hydrogens are automatically added. These are the polar hydrogens. These are added to the protein. So this is the most crucial step prior to the docking. If you want to prepare the protein for molecular docking, then you need to add hydrogens to the protein. So this is how this can be done automatically. You don't have to do anything, just you have to focus on the protein, which is the target, and you can do these structural modifications prior to the docking. So this is how you prepare the protein. So now I'm going to close, and you can see if you open this by using a text editor, you can see that this is a mol2 format. This is the numbering. These are the atoms. These are the XYZ coordinates. This is the naming convention from the Chimera using the amber force field. This is the protein, and this is belongs to this particular section of atoms belongs to serine, and these are the charges associated with this. So this is how you prepare the protein prior to the docking. Now I'm going to show you. So this is one approach how you can prepare the protein using UCS of Chimera, and also you can open this again using Chimera. And if you want this particular protein to convert into PDB-QT format, then go ahead, file, save PDB. It's just 6lu7 modified. So this will be saved as PDB file over here. You can see the difference between the mol2 and the PDB file as well. So this is the mol2 version where charges are written, and this is the PDB file where there will be no charges written to this, because PDB doesn't contain all the charges written on the file. So basically these names, the naming convention of this came from this particular mol2 file, and these are the atomic coordinates, and these are the names of the atoms. Okay, so this particular modified PDB, which contains the hydrogen atoms, you can use in MGL tools. So as I mentioned earlier, if you have installed the parallel, you can use Windows inside the Mac. So if you have installed already the MGL tools, so this is the version 1.5.6, the icon looks like this. So if you open it, there will be an option called register now. You can register by giving inputs of your email ID, your name, and your university name, and you can register your version of AutoDock Tools in this particular section. And I'm not going to show how to do that. You can do it by yourself. So just click remind me later. So this is the the window, the GUI platform of AutoDock Tools, or which I call MGL tools. So here, if you go here, file, read molecule, and I think you have saved in your desktop. You can see, so, there's a PDB and a protein data bank file, PDB file. You don't need to open the mol2 file, because mol2 file won't open inside the AutoDock platform. So you have to click on that 6LU7 PDB file, modified one, and you can see the white color. These white sticks are nothing but the hydrogens. But if you haven't used Chimera at all, there is another way that you can prepare your protein structure, and you can do a lot of structural modifications prior to the docking. But before that, I recommend everyone to open your protein and delete all the non-standard residues before going to do some structural modification in MGL tools. So I'm going to show you how to use MGL tools for the protein preparation wizard. So I'm going to do it again. So let me close this window and let me open the 6LU7 PDB. Sorry, this is Chimera X. You can open, if you are not using Chimera for the protein preparation, you can follow these steps. So open the structure in Chimera, select residues, the non-standard residues, action, atoms and bonds, and then delete. Okay, then select chain. You need only A chain, you don't need the C chain, so click on C chain. It has been highlighted, and action, atoms and bonds, delete. So now this is the pure form of the protein, which doesn't contain anything. The water molecules and all the non-standard residues have been deleted, and the chains have been deleted. So go ahead, file, say PDB, and name it as 6LU7 something underscore mod. Sorry, underscore mod. Okay, this is you save it on your desktop, and if you go here, 6LU7 mod.pdb, and now you open the MGL tools. Yeah, it takes some time to open the GUI. Yeah, this is how you open the MGL tools, and go to file, read molecule, go to the desktop. I think 6LU7 mod. Yeah, this is the protein data bank file. Okay, so there are no hydrogens in it. You won't see any white sticks over here. So the first thing that you do over here is go to edit option and delete water. So click on this. If you have any water molecules, you can delete all the water molecules. I'm not going to deal with the hydrated docking or the metal docking now. This is a simple basic docking that you can perform by using MGL tools. So now what you have to do is add the hydrogens. So go ahead, the hydrogens, add, and here now there are all hydrogens and there are polar hydrogen. So you can click either on all hydrogens, and then later on there is another step that you can merge the non-polar hydrogens, or else go ahead and click on polar only. So if you click on all hydrogens, okay, so hydrogens will be added to the whole protein. And if you go here, hydrogens, again there is an option called merge non-polar, that you can click, and you can see that the non-polar hydrogens which are attached to the carbon or hydrocarbons, they will be deleted, and only those hydrogens which are I think attached to nitrogen, they will be present over here. So that's the advantage of using this particular option. So basically the united atom model simplifies a docking by reducing the overall number of atoms to be considered. So you don't need much more hydrogens to be considered prior to the docking. So this is particularly accomplished by merging the non-polar hydrogens with the carbons to which they are bonded. So basically the hydrogens which are bonded to the carbons are merged, and only the partial charge of each non-polar hydrogen is added to the charge of its carbon, and then the hydrogen is eliminated from the molecule. So this is why you use the merge nonpolar hydrogens, which is very beneficial, and the computation power will be, I think the resource will be reduced, and the computational time will be reduced by using this particular option. So this is how you know prepare or add hydrogens to your protein. And the next step would be go ahead and click on charges, and you put add Coleman charges. So this particular Coleman charges is used only for the macromolecules. So why is that? The main difference, there are many different charges. So there are two charges which are associated. One is compute Gastigier charges, and another one is the Coleman charges. So for the macromolecules, we generally use the Coleman charges, and for the ligands or chemical compounds, we use the Gastigier charges, as we have shown previously in Chimera during the protein preparation. You might have seen the Gastigier for non-standard residues. So that's why we use only Coleman charges for the macromolecules. The main difference between the Coleman charges and the Gastigier charges are template values for each amino acid that were derived from corresponding electrostatic potential using the quantum mechanics, whereas the Gastigier charges are determined on the basis of electronegativity equilibration, which can be computed by these particular AutoDock tools for the given molecular system. You can use Gastigier charges for the protein since both approaches yield similar atomic charges. The only problem is that the Gastigier method assumes an overall net neutral state for the respective molecular system. So before adding the charges, check the protonation states of the amino acids and the particular chemical compounds. And I have been using this particular approach by adding the Coleman charges to the macromolecule for all my scientific publication and for all my research work. So I had good success using Coleman charges for the protein and the Gastigier charges for the ligands or any other cofactors. Okay, so, and if you don't add the charges, if no charges are added to either to the ligand or to the protein, then all the electrostatic interactions between the protein and ligand will be absent, and van der Waals forces or van der Waals interactions will become dominant. So that's why you need to add respective charges to macromolecules and to the ligands. Okay, so this is how you prepare the protein structure. And now moving on, for the AutoDock Vina or for the AutoDock 4.0, you click on the grid and choose macromolecule, and here go to choose and click on the particular molecule, select molecule. So here it will show a warning. You have to ignore that because this is initializing the PDB file which contains no non-bonded atoms, because all the atoms have been bonded, and now our protein is ready for the molecular docking approach. So click OK, and it will be saved as PDB-QT file in your home directory. If you want to save it on desktop or anywhere, you just go ahead and save it as .pdb-qt file. So yeah, this is how you prepare the protein for molecular docking prior to the docking. So this is the protein preparation wizard, I would say. So this is how you prepare, and if you just have to quit it, and if you go to the files and folders, yeah, so I think this is located over here. Let me see. Yeah, so I think, yeah, this is the PDB-QT file in Windows. I think it will be accessed over here. If you go to the PC local disk, users, and yeah, if you go here, you have the file pdbqt. So go ahead and copy this. I'm going to copy this, and let me close this window, and let me open over here. Oh, I think it is closed. Let me see where it is again. Yeah, go to the folder location. It is, if you save the pdbqt file, it's generally saved on your users folder, which is the home folder, I guess, for Windows. And yeah, this is the pdbqt file. So go here and save it. Yeah, it is saved now. So you can close window and open this by using any text editor. So I'm using Sublime Text, which is very good. So this is the pdbqt format, in which the atom, the numbering of the atoms, these are the atoms, these are the residues. This is a chain A, because we have only dealt with chain A, not the C. I think this is the residue number, residue 1, residue 2. These are the XYZ coordinates, and these are the charges associated with this. Okay, and these are the naming convention of the particular atoms. This is how the pdbqt format looks like, and this pdbqt file, if you want to open using Chimera, you cannot open it because it doesn't support pdbqt format. For that, you need to use Chimera X, because Chimera X supports the pdbqt file, and if you open this, you will see the pdbqt file of your pdbqt file by using Chimera X. So if you want it soft, or let it be a black background, it looks, this is how you prepare the protein. And if you want to show the atoms, you can show the atoms, and these little sticks of white sticks are nothing but the hydrogens. Yeah, you can zoom in and you can see these are the hydrogens added to the protein, and the charges have been automatically assigned by using AutoDock Tools. So yeah, this is how you prepare the protein for molecular docking approach, and this is the best way that you can prepare the protein. Okay, so that's it for today. I'm going to deal with the ligand preparation and the grid box, and in the next video I'm going to show the AutoDock Vina, how AutoDock Vina works, and what are the parameter files that you require in order to run the calculations. So see you in my next video. Thank you very much. In silico methods are extremely useful for both finding potential binding sites and also to discover or engineer new molecules that could bind to a known site of the target. The purpose of this practical is to give a flavor of how one could dock small flexible molecules to a protein structure. This is a multi-billion-dollar industry. Virtual screening and the blind docking are often employed in an attempt to discover new medicines. Hello everyone, this is Preetham. Welcome to the series of molecular modeling and drug designing. Today I'm going to talk about the ligand preparation or the drug molecule preparation. The reason why I'm showing this slide is I have added two more software, which is Avogadro and another one is the ChemSketch, in which you can download the drug molecules from different databases. As we referred from the paper that we took the target of the protease protein of COVID-19, and the target that we are going to see, we can download it from different types of databases, and we can process it in order to do the molecular docking analysis using Vina software. So the basic requirements are MGL tools, Vina, Avogadro, and even you can use ChemSketch to define or to derive the structural information of the drug molecule. So yeah, let's get started. So I'm going to show you, this is the paper that I referred previously, and this is the drug that we are going to look over. If you Google it, so you will find this drug as nirmatrelvir. This is antiviral medication. This is developed by the Pfizer, and which acts as an orally active 3C-like protease inhibitor for COVID-19. Okay, so if you see the Wikipedia page of this particular drug molecule, you have different types of links, in which the first link that you go here is PubChem. So if you click the ID, it will redirect it to this page, which is from the PubChem. So generally when we do molecular docking analysis, the most referred online site is PubChem. This is from National Library of Medicine, provided by NCBI. So this contains all the information regarding the ID, the 2D structure, the 3D structure, the chemical formula, and different synonyms of them, different names in which it is sold, the molecular weight, and the description of the drug. And this is what the 2D structure looks like, and this is what the 3D structure looks like. Okay, so go to these databases, this database, particular database PubChem, and here you have the option to download the structure of the molecule. Do not download the 2D structure, because you don't need the 2D structure to be docked to the protein target using AutoDock Vina or any molecular docking program. You need the 3D optimized structure. So if you want to investigate this 2D structural form, then you can use different types of softwares like ChemSketch or Marvin Sketch, those kind of chemical structure modificational software. But generally for molecular docking analysis, you require the 3D structure. So I'm going to show you how to open the structure in UCSF Chimera and process it basically. So if you go here, you can download the STF format, because JSON format or XML, ASNT won't be opening in Chimera software. So you have to go and download the STF file. So once you download the STF file, so this is the STF file. This is the ID with the conformer, that is 3D conformer, and this is the ID of the molecule. So go ahead and rename it to 12V. Okay, if you go ahead and open with Chimera, so the STF file is supported in Chimera. So this is what the 3D structure looks like, and you can name it as well. Go to the label and element. Yes, you see the white colors are the hydrogen, these gray colored are the carbon atoms. This is fluorine, the green colored one, and always in Chimera the red color is oxygen, blue is nitrogen, white is hydrogen, and the grayish, I would say, is carbon atoms. And rest of the molecules, they will be colored different types. Like in this case, the fluorine atom is green color. Okay, so this is the way that you can open an STF file inside UCSF Chimera. And if you need the PDB structure of this, go ahead and save as PDB. So yeah, per se I say drug. In desktop I'm saving it. You can save it as PDB file, and also you can save it as you can save it as mol2. Save as mol2. Yeah, you can save as drug mol, let's say. Okay, so this is how you save the molecule, by opening the STF file in Chimera and save it as PDB and mol2. So if you go to the desktop, I think yes, you have the information over here. This is the mol2 file, in which you can see the Mol2 file, and these are the charges associated with it. These are the atom numbers, names, the coordinates, and the naming convention of the Mol2 file. And this is how the Mol2 file looks like. Also, if you go to the PDB file as well, yeah, this is the PDB file. I think I've saved it as drug, yeah, drug.pdb. So this is the PDB file, again the same, but no charges are written in the PDB file. Okay, so this is how you can save it. And then next important thing is, if you go below to these databases, you have different types of descriptors. Okay, so the most important thing that you require if you need any structural if you want to do some structural modifications, the most important thing is you require the canonical smiles. So I'm going to show you another software that I mentioned before, that is ChemSketch, in which how you can modify the ligand. So if you let me show you the ChemSketch database. This is the ChemSketch database in which you can go and download the download the software for academic and personal use. You have to register, and the software will be downloaded. And this is only, the ChemSketch is only available for Windows. Mac users cannot use this software. I think it is only specific for Windows users. Okay, so if you go to Windows and type in, I've already installed and downloaded the ChemSketch. So this is how the ChemSketch looks like. This is the freeware version, or personal use, for the personal use. Okay, so when you open this, you have different types of tips. It will show different types of tips how to do that. So go ahead and to the PubChem database and copy the canonical smiles over here. And if you go to the tools section, there you have the option generate structure from smiles. Okay, yeah, I have already downloaded this, so I'm going to paste over here and click OK. So this is how the structure looks like. Okay, this is a bit messy, so if you want to clean it up, then I think this is a clean structure. Yeah, this is the option in which you can clean the structure. Yeah, so if you clean it, it will show the 2D representation of the drug molecule. And if you go to the tools, and if you want to do the numbering, you can do the numbering where it starts from here and it goes like this. Yeah, this is for the chemistry people. I think those who are biochemists, they are more likely to use this software more often to modify the structure or add something, add the functional groups, and many structural modifications can be done here. So if you go again, and there is an option called 3D structure optimization. If you click that, you have this is the 3D structure. You see the hydrogens have been added automatically. So this is how the 3D structure looks like. And also you can name the structure by clicking the name for the structure, and you will see, I think this is available for the for the commercial version, maybe, I don't know. I mean, there is a video regarding how to name the structure, and I think if you draw the structure over here, not by getting the canonical smiles or PubChem from the PubChem databases, I think you can name the structure basically, and you have the option to download from the PubChem directly. So if you want the exact structure or substructures, you can download from PubChem, eMolecules, I think ChemSpider. These are the 3 databases from which you can download. Okay, so this is the 3D structure, and if you want to save it, then export and you will see that you have different types of options like .mol, skc. I think the pictures can be also saved. I think the mol is the one of the format that you can save if you want to open in UCSF Chimera or PyMOL or Avogadro, etc. Okay, so I name it as drug.mol and I save it in desktop. Yes, and go ahead. So this is how you can use the chem sketch and you can modify the structure according to your needs. And yeah, that's all about this software. So I'm going to close this. Yeah, and you can see that my drug.mol file has been saved. So if you go to the, yeah, this one is saved. So if you go to this if you open it by using the text pad, then you will see this is the mol format, and the previous version which I've shown is mol2 format, which contains all the charges, and this is the mol format basically. So if you open by using let's say Chimera, you can see the hydrogens have been automatically added and the structure is optimized, I would say. And another software that I mentioned before is Avogadro software. So if you go to the site Avogadro, yeah, this is the free molecular editor. You can download it for Mac OS and Windows and Linux as well. So this is one of the best software for computational chemistry, molecular modeling, and bioinformatics, as well as material science also. So this is a free and open source software, one of the most widely used software for material science and bioinformatics. So if you click on the molecule and use Avogadro, you will see, since I saved the 3D structure of the molecule, this is now saved. Yeah, this is a 3D molecule. You can zoom in, zoom out, and there is an option over here. If you can add hydrogens and add hydrogens for different types of pH also. In the build section, this is the Cartesian editor where you can modify XYZ coordinates, and in the extension tab you have the option to optimize the geometry of the molecule. So before doing any molecular docking analysis, so it is recommended to optimize the structure of chemical structures in order to get better binding poses or better interaction with them and accurate interaction, I would say. So go ahead and click the extension tab and optimize geometry. You will see the structure will be optimized based on different types of molecules that are present. So until and unless it is getting stopped, you have to click optimize, and you see that the fluorine atoms over here, they are getting optimized, and optimize it. You see the optimization is based on a certain force field that is inbuilt in Avogadro. So again, optimize it, and the moment where you see that there are no more modifications or no animations that is going on, you can optimize it. Yeah, and see now the structure is fully optimized, I would say. So go ahead and file and save as. It will take some time. Yeah, you can save as PDB, you can save as mol2 as well. So let's save it as PDB file in the desktop. Just type in drug Avogadro. Yeah, this is the PDB file. Okay, I save it and close this. So now you have the drug Avogadro. Use the Sublime text to see the optimized geometry, the optimized XYZ coordinates, etc. And if you want to open any molecule and you want to save it for further molecular docking or any bioinformatics analysis, I would recommend Avogadro is one of the best software that you get a clean version of the PDB file, and also Discovery Studio Visualizer, that is also a good software. Chimera also provides Sybil format or MOL2 format as well. So, but I recommend to use Avogadro for any for saving the molecules for different bioinformatics analysis. Okay, this is how it looks like, and if you open the drug by using UCSF Chimera, you will get it. Yeah, this is how it looks, and you can design this. This is the final optimized structure of the drug molecule. Okay, now we go ahead and I think we open this particular structure by using NGL tools. Click on the AutoDock Tools. Now we can modify the drug molecule in order to dock the structure by using AutoDock Vina. Yeah, when the window opens, so now you don't have to go to File, Read Molecule, etc. But there is an option here that is called Ligand. So go to the Input section and open the molecule. Let's see if you have the, go to the desktop, and here you always see the default file opening in ligand section is PDBQT. So change it to PDB files and you will see the PDB molecules. So the latest optimized drug molecule that I've saved from Avogadro is drug Avogadro, and click and you will see the drug molecule. So the summary of the drug molecule will be automatically, there will be added Gastigier charges. 29 non-polar hydrogens have been merged. It found 3 aromatic carbons and detected 11 rotatable bonds. The torsion has been set to 8, which is the default one, and it has 11 rotatable bonds. Okay, so once you open this and once you click that, all the non-polar hydrogens have been merged. But if you open any drug molecule which is downloaded directly from PubChem database or ChemSpider or CHEMBL, so once you open the structure here, the PDB format, then go to the edit section and add hydrogens. Okay, if you are not sure that the hydrogens have been added, so go here and add hydrogen. You see all hydrogens have been added over here, and if you save it to PDBQT format, it will automatically merge the non-polar hydrogens. But if you can do also here like merge non-polar, you'll see the non-polar hydrogens have been merged, only the polar hydrogens have been retained over here. And if you're not sure that you have added any Gastigier charges or any other charges have not been added, then you can do it here. Yeah, you can see that total Gastigier charges added are this much. Okay, another important thing is if you go to the second option that is called torsion tree, and there is one option called detect root. You'll see a green spear will be popped up, and this is the route from where the molecule will try to bend whenever any optimization or molecular docking analysis. If you do any molecular docking analysis, then this is the point where the molecule will be bending in order to interact better, or maybe it create different types of poses. So this is important that you detect the route from where you can bend the molecule. And if you go to the torsion tree and see choose torsion option, and you will see that The red ones are the unrotatable ones. These cannot be rotated. The green ones are the rotatable ones. That's why the root is over here, and you will see that this particular instance of the carbon-carbon bonds will be rotated, and these aromatic rings will not be rotated because these are in red colors. Okay, so it is said that number of rotatable bonds 8 out of 32. So maximum rotatable bonds which is allowed in MGL tools is 32. But when you first open the molecule, you have seen that there are 11 rotatable bonds, and the magenta are non-rotatable. If you see, these are the magenta color, which are non-rotatable. Non-rotatable. Okay, so if you can, there is one option called make all active bonds non-rotatable. You can click here, and it will set all the rotatable bonds to 0. And if you click again, you will see that number of rotatable bonds in this particular molecule are 11, which are in green color. Okay, so click once and click again, so that you will see the number of rotatable bonds over here. You can modify this also. If you click over here and then select this particular instance and make it unrotatable, just click and make it unrotatable also. Okay, and now you can go and save it as save it as PDBQT format. So I'm going to go and save it as okay. The name is drug avogadro.pdbqt. Go ahead and save it. Now the preparation of the ligand molecule for molecular docking Vina has been prepared. So this is how you can download all the molecules and prepare using MGL tools, modify, optimize the geometry, and then finally open it here, save it as PDBQT file. Now let's go ahead and see the structural file, how it looks like, the PDB file. If you this is the PDBQT format of the molecule. I previously mentioned that the PDBQT format of any drug molecule can only be opened by using UCSF Chimera X, not UCSF Chimera. Chimera doesn't support PDBQT format. Okay, let me open Show in Finder. Just save it and open with text editor. Yeah, you see, it will automatically show that it has 11 active torsions, and these are the 11 active torsions. This is the number of torsions, 1 to 11. A means active, I means inactive. Between N1 and C12, C10 and C22, C12 and C24, the number of torsions have been written over here in this PDBQT file. And if you go below, so generally the drug molecules or any chemical compounds that you save as PDBQT format, or even in PDBQT format, you will see that it will be named as heteroatoms, not the atoms. Only the atoms are named for protein residues, amino acid residues. So that will be named as atoms, but any other chemical compound which is not the amino acids will be written as heteroatoms. And these are the numberings, the naming conventions, and this is the name UNL. UNL means unknown ligand, or UNK sometimes, or you can name it later on by modifying the file. And these are the coordinates, and these are the charges associated with this. So remember one thing, that when you save any molecule that is derived from any databases like PubChem, ChemSpider, CHEMBL, the PDB file do not contain any of the charges associated with the molecule. So it is recommended that you save it as mol2 file or mol file that I have prepared using Avogadro by optimizing the geometry of the molecule. Then open the mol2 file in MGL tools, or you can also take the PDB files also, but I recommend you to use mol2 file because it has charges associated with that, and save it as a PDBQT. In here I have shown the PDB, how to do the conversion from PDB to PDBQT, but always I recommend for any drug molecules or for any chemical compounds, please go ahead and save it as mol2 file, because the charges will be written, and you have to check whether the charges are correct or not by optimizing it and by making some structural modifications. So yeah, this is all about the ligand preparation, and you can save it as PDBQT format. And yeah, that's it. In the next video, I'm going to show you how to prepare the grid box for the protein molecule that we prepared last time, which we saved as I think a PDBQT file. I'm not sure where I'm. Yeah, I think where PDB. Yeah, this one, the PDBQT file, the protein molecules PDB, the protein molecule PDBQT file, and we can open this molecule in MGL tools and prepare the grid box. In the next video, I'm going to show you how to do the grid box and do the final molecular docking using AutoDock Vina. So see you in my next video. Thank you very much. Hello everyone, welcome back to my channel. Today we are going to learn how to prepare the grid parameter file or the grid box for the PDBQT file that you have prepared by using PDB files and by learning it from my previous videos. So this AutoDock Vina, they generally require the grid maps for each atom type, and they help to make the docking calculations fast, and this particular grid map consists of three-dimensional lattice of regularly spaced points surrounding either entirely or partially and centered on some region of interest of the macromolecule. So if you don't know the binding site of the macromolecule where the drug molecule interacts, then generally people they approach the blind docking approach where they cover the whole protein by using the grid box option in MGL tools. But when you know the interacting residues and some key residues that are involved in the interaction of the drug molecule, then people generally use targeted docking. So let's get started. I'm going to show you how the MGL tools works on PDBQT files that you have prepared previously, and how you can open by MGL tools. So let's go ahead and open the Windows, use the AutoDock Tools GUI. I'm going to show you how to open the PDBQT file that you have saved earlier, and this is the box, and go to the file menu, read molecule, and go to the desktop. Here I think I have created a folder called Vina. There I have saved the PDBQT file, the drug file, and all these things I'm going to tell you in a bit. So go ahead to the folder, and this is your receptor file, and generally in Windows they name it as AutoDock structure file, or these are AutoDock supported PDBQT files. Okay, go ahead and open it. So here is the protein with the non-polar hydrogens that are merged, and polar hydrogens are only present over here. If you want to display it as CPK, you can just go to the display menu and click the CPK version, and if you want to display only by sticks and balls, then go ahead and apply here. I think you have to switch it off over from here, and here it looks this is the ball and stick model, I guess. Okay, so I'm not going to show you how to design the protein or how to represent a protein, that because that is not important over here. The important thing is how to prepare the grid box. So go to the grid option. Here you can see the grid option. Go to the macromolecule, choose and select the receptor. Okay, here it says that the PDBQT file or the protein structure file have already the partial charges, because previously we have added Coleman charges to the macromolecule. So it asks you that do you want to preserve the charges instead of adding the Gastigier charges? So click yes, you want to preserve the charges. Okay, so this is how you open the macromolecule by using the grid option. Then now go to the grid box option. Okay, now we are going to do the blind docking. So typical grid point spacing, it varies from 0.2 angstrom to 1 angstrom, and the default value is 0.375. So this particular window consists of the file section, where by choosing the grid points you can save it, and you can just write it to a text file also. And center option, it contains when you pick an atom, or if you have any bound drug molecule or chemical compound or ligand to the macromolecule, you can just center it on. And there is an option called center on macromolecule. If you don't know anything, just center it on macromolecule, and you can also center it on a named atom. So this particular option, named atom or pick an atom, center on ligand, this works for the targeted docking. For the blind docking, generally what we do is, so this is here the grid box. The red color one is the grid box with the marker size, that is plus. You can just adjust the marker size to, let me make it to 2.0, and you can see there is a plus sign with increased size. Okay, this is now the grid box, the red one, which is centered on the macromolecule. And these are the number of points in X dimension, Y dimension, and Z dimension. And this is the grid box center. This is the center of the grid box, which consists of coordinates -26.283, 12.5, and 58.9. So X center, Y center, and Z center. Okay, so the maximum number of points that you can increase in all the direction is 126. So if you right click on this, right click, not the left click, right click on this, you have this option pops up. So the maximum that you can enter is 126. Okay, click here and apply. Okay, you can see the box has been increased in X dimension until 126 points. Okay, go ahead, do the same with the Y. Remember, this is we are doing the blind docking, not the targeted docking. Okay, and Z dimension, you make it to 126, apply. Okay, so this is do not close this box until you have finished preparing the grid file. Okay, so once you have entered the dimensional points, that is 126, you can see that some of the portion of the macromolecule, they are left out. They are just not fitting under this box. So the next thing that you can do is you can increase the spacing angstrom, and 0.375 angstrom is the default one. You can just right click over here and you can just change it to 1.0. Okay, and click on apply. So as you can see, the box has been drastically increased. I mean, this is a very big space, a big grid box with a lot of search spaces. But I don't think so you need that, because this is too big for this small macromolecule. What you can do is just by using your left mouse button, you can just decrease it. As you can see, you can decrease, and here you can increase. So you can adjust the spacing angstrom based on your macromolecule, just to see that whether the macromolecule is fully covered or not. And even I think you can even decrease it, because it is being covered with 0.5, I guess. I guess this is good enough. Okay, this is how you prepare the grid box for the blind docking purpose, because you are covering the whole molecule. Okay, so the next thing what you have to do is go to the file and output grid dimension file. Okay, so go to the specific folder and just save it as grid.txt. Okay, I have already created it, so again go ahead and it will be saved as grid.txt. So if you open the grid.txt, you have the spacing of 0.583. Compare it whether this is correct or not. The number of points 126, 126, 126. The center is you see the coordinates that exactly saved in the grid.txt file. Okay, so this is how you prepare, and this is for AutoDock Vina purpose, that you don't have to go ahead and close saving current. You don't need that, because you don't want to save the parameter file for any other program. The AutoDock Vina, it requires only these two things. I mean these three things: spacing, number of points, and center. Okay, so you just close it. This is for the blind docking. Again, I'm telling you, this is for the blind docking. Okay, so now if you want to do the targeted docking, then targeted docking is nothing but if you know that your drug molecule is interacting with specific residues. You click here in this tree, and you have this A chain, and these are the residues. Suppose per se you find it in some papers, you find some of the amino acid residues of this particular macromolecule that are interacting with specific drug. So if you know those residues, suppose you take arginine 131. Okay, if you click these residues, it will be selected. I think it will be highlighted in yellow color, or what you can do is just select it and display as CPK. Okay, now yes, you can see that this particular CPK that has been selected over here, it is arginine 131, and you don't want to do the blind docking, because you already know the specific residue that is interacting with your drug molecule or chemical compound. So this is we call as targeted docking. So what you do is, so if you go to select and just hover your mouse over here, you can see that how you can write specific residues or specific atoms. Okay, so if you click double colon and CYS star, then it selects all the cysteine residues, and it will be selected, it will be highlighted over here. So if you click triple colon CA, it selects all the alpha carbon atoms and sets the selection level to the atom. Okay, and if you click single colon A, which is chain A, and double colon CA, it will select all the CA in chain A. Okay, this is how you can select particular residues. So now you can do that by using this particular mouse, and by clicking on these boxes, it will be selected. Or else, if you don't want to do that, then just go ahead and double colon. Suppose this is arginine 131. So if you do that, it will be selected. You see, if you enter this command, it will be selected. Now go to the grid and grid box, and here there is an option there is an option to center it on a named atom. So here you exactly write the same command or the same argument where you have done the selection ARG131. okay, just click it. So you'll see the grid box has been shifted. So now for the targeted docking, you don't want to cover everything, so the default dimension for the targeted docking or for the AutoDock, the default one is 40. So go here and click 40. Okay, and similar with this, go here and click 40, and go here and click 40. Okay, now you can see that your box is comparatively smaller than your blind docking box, because blind docking, it covers the entire protein. But when you do the targeted docking, you see the box is only centered on arginine 131. Okay, go to the file section and output grid dimension file, and just save it as grid targeted dot text. So this is your grid dimension file for the targeted dock. You see the points have been reduced, the spacing extrom remains the same because we have reduced the box, the number of points, and this is your X center, Y center, and Z center. So when you compare with the blind docking, you see there are some changes with the XYZ center or XYZ coordinates, because you have selected one particular residue and you have shifted the grid box by centering on that particular residue. Okay, this is how you prepare the grid box, and I think in this tutorial I'm going to end this because this grid box is really important parameter to do the AutoDock, or maybe AutoDock Vina, because it creates the search space in which the AutoDock Vina program runs. And if you compare the blind docking and targeted docking, the blind docking takes so much time because the search space is the entire micromolecule. But when you do the targeted docking, the search space is very small, so it takes less time in comparison to the blind docking. So in the next video, I'm going to show you how to prepare all the files in order to run AutoDock Vina. Thank you very much. Hello everyone, welcome back to my channel. In this particular series, Molecular Modeling and Drug Designing, today we are going to do molecular docking using AutoDock Vina. Previously, I have shown you how to prepare the protein, how to prepare the ligand or the drug molecule, and how to prepare the grid box for the macromolecule that I've shown. So today we are going to do the final docking by using AutoDock Vina. So AutoDock Vina, I'm going to show you the release of the new version of AutoDock Vina, that is 1.2.0. This is published in I think JCIM. Okay, and this particular AutoDock Vina is quite improved and very fast in comparison to AutoDock Tools, which uses this 84 program. And this particular algorithm implemented in AutoDock Vina uses Monte Carlo and BFGS breadth first search algorithm, and this is the paper related to the new version of the Vina. And some of the important points that you can extract from this paper are written over here, and there are some of the features which are implemented in AutoDock Vina, in which one important parameter is the exhaustiveness. So it varies from 8 until 64. Okay, so it was written over here that Vina scoring function using the exhaustiveness of 64 and a linear potential of 50 kilocalorie per mole per Armstrong were good in comparison to 84 having the surge exhaustiveness of 8 to 64. So it is recommended. So from this particular table we can extract the information that if you are using AutoDock Vina force field, then you can extend your exhaustiveness from 8 to 64, and 64 gives you lowest RMST, root mean square deviations, and using high exhaustiveness improves the search algorithm and better performance in comparison to 84 scoring function, which is implemented in AutoDock Tools. I mean AutoDock 4. Okay, and another important thing that is written over here is that the score is calculated on the basis of intermolecular interactions plus the intramolecular interaction and the intra-best interaction minus intra-best interaction divided by 1 plus 0.05846 into number of rotations. So in Vina scoring function, the intra component only cancels out exactly for the first pose. The first pose or the binding pose that you get from AutoDock Vina is always the best in each docking run. If the attractive potential of the macrocycle ring closure is different across poses, all poses except for the first may be impacted by it. So basically there are different types of modes in AutoDock Vina. You can vary until 100. So the optimum interaction range, there is no optimum interaction number of poses or number of interaction range. So basically we generally give n is equal to number of modes is equal to 20. 9 is default, I guess. Yes, 9 is default. But you can increase it until 100, 200, 300, depending on your needs. So in this particular tutorial, we are going to use n is equal to 20, which is good enough. And I think exhaustiveness, we can vary from 8 until 64. I'm going to show you one example with 8. How much time does it take when you put the exhaustiveness to 8? And if you put exhaustiveness 64, then it will take much more time, but it has better performance in comparison to 8. Okay, so this is the paper. I recommend everyone to read this paper, which describes the force fields, the different types of scoring functions which are implemented in AutoDock Vina 1.2.0. and yeah, here is the website where you can go and download the AutoDock Vina. Since I'm using Mac, so you can download this. I have already downloaded the tar file and I have extracted it. So in here you will find Vina and Vina underscore split two binary files, executable files for the Mac. And the latest version of the AutoDock Vina can be downloaded from GitHub. So if you go to the GitHub, these are the old versions. So if you go to the GitHub directory, then you find the latest version. This is for the Mac. If you download this, yeah, okay, yeah, this is for this is the latest version for the Mac OS. Okay, so I have already compiled everything over here. I have created a folder as I have shown previously, and these are the two executables which are based on the new version. Okay, this is, I think this is the new version. I have used this particular version, I think, but this is the latest version. But I don't think that there are major changes, but whatever the changes are implemented, those are written over here. I mean, there are some minor fixes. Okay, So you can go ahead and download it, and Windows users can download the .exe file, and Linux users can download from here. These are the executable files. Okay, and also you can download the source code, which you have to install by using command line interface. That you can let's open that. I think, yeah, you can build for Mac and for the Linux and for the Python, and how to do it has been written in this particular readme text file. Okay, so this is how you go and download and read the paper if you are interested in knowing the potentials or the force fields which are used in AutoDock Vina 1.2 version. Okay, and I would recommend to read the paper and extract information that is needed for you regarding the algorithm, the scoring functions, and a lot more. So let's get started with the AutoDock Vina executable. Okay, so let me close this. And yes, one more thing, that if you downloaded the AutoDock Vina for the Mac OS, so if you try to open it, so open your command line, navigate to the directory. I can increase, yeah, navigate to the directory, and the command for the Mac executable starts with /Vina. This is a basic Unix command. So if you type /Vina, that means this particular executable we are executing, /Vina. So it will show that Vina cannot be opened because the developer cannot be verified. Okay, so what you can do is, for the Mac users only, go to the settings, system preference, and go to the security and privacy. Okay, and here you can see that Vina was blocked. Okay, so you can go ahead and type the password. Okay, and click here, allow anyway. Okay, now close this and cancel it, and again you type Vina. Yeah, and the option open will be popped up. So open, and now you get your Vina executable executed on Mac OS version. So this is the command line argument.vina, and these are the commands that you can give for the new version of Vina. So if you want to check the version, then /Vina - version, and you can see that this is the version 1.1.2. So I think you can download the latest version and apply the same by using the same command, and the way that I've shown here you can execute if you are using the latest version of Mac OS. Okay, so here it is. So let me close this, and we navigate to the directory where I have saved the receptor, the 6LU7 receptor, and this is the drug molecule. And yesterday when I was doing the grid box for the macromolecule, I have saved 2 grid boxes. This is for the blind docking, and this is for the targeted docking. Okay, so one of the main important parameter in order to run the AutoDock Vina is the configuration file. So basically the configuration file consists of center X, center Y, and center Z, and these are just the coordinates you have to give, size X, size Y, and size Z. Okay, so let me, yeah, and if you open the blind docking grid box, okay, so the spacing is 0.583, number of points is 126, so you can put size X is 126 here, 126, size Y is 126, and put the coordinate minus 26.283, 12.599, and 58.965. okay, so this is for the blind docking, and remember the spacing 0.583. okay, so this is the configuration file. You can save it by using by renaming it to conf.text or any name if you like, but generally we save it as configuration.txt or conf.text. Okay, so now go to the command, now go to the blind docking and copy the conf.text which you have recently saved. Okay, this is the conf.txt, this is the receptor file, this is the drug molecule, and these are the two executables. I'll tell you how to use the Vina underscore split. So first use the Vina and then we can use the Vina underscore split. So go to the directory blind docking and navigate to this directory by using the command line. Let me increase the size. Okay, the command for using a command to use the AutoDock Vina for docking purpose is /Vina. This will execute the Vina executable file, and --, receptor, which is your 6LU7. If you press tab, it will automatically come up. Okay, and then your drug molecule or ligand, that is drug avocado.pdbqt, and your config file config, and your config file name is conf.text. Okay, and then your exhaustiveness. Okay, your exhaustiveness. So I mentioned before that it can vary. The default value is 8 to 64. So we start with the 8 exhaustiveness and we'll see how much time it takes. Okay, and then out file will come as --out, which is you can name it as 6LU7 with drug molecule .pdbqt. Okay, that will be your output file. I mean, all the binding poses will be saved over here in this particular output file. Okay, and then the next command is number of modes. Number modes is equal to, as I mentioned before, generally the default is 9 or 10, I guess, but for exhaustiveness 8, I use numbers 20. Okay, and spacing. So you give the spacing, as I have shown you before, that spacing is 0. I think here the spacing is 0.583, so that you have to input over here 0.583. Okay, this is the spacing. So this is the default command. So if you press enter, you will see the box, the AutoDock Vina version 1.2.2. I think this is the latest version, and this is the citation of the paper. The scoring function is Vina. This is the default one, Vina. This is the receptor, this is the ligand, this is your center, this is size, this is grid space, exhaustiveness is 0. CPU, you can mention if you are using parallel version or MPI version, you can give CPU. And verbosity, I'm going to explain what is verbosity, and you will see how the results change if you change the verbosity. So you will see that with exhaustiveness 8, it almost took maybe 40 to 45 seconds or 30 seconds, maybe 45 seconds, and you get all the values. So this is how you run the AutoDock Vina by using the configuration file and different parameters. So the first thing is different types of modes. Since we have input, I can show you the command, that is number of modes 20. You get the 20 poses starting from 1, and this is the affinity or the binding energies, which is in kilocalories per mole. And the first pose is the best pose, as it was mentioned in the paper, which is having the RMST 0. RMST, this is the lower bound and this is the upper bound. So it starts from 0, and you can see that whenever the when you have different poses, then you have different types of RMSTs in comparison to the first pose Okay, it is always compared to the first pose. That is, 0 is compared to all different all different poses. Okay, so this is the basic command. Okay, so clear it out, and again, if you go by help, advanced, okay, so if you click, then you have different types of option, right? So these are basic options that are those are receptor, ligand, and batch ligands. If you have multiple ligands, then you can also do that. I'm not going to show how to do the batch ligand here because we are focusing on one ligand, and this is particularly the blind docking. And we have different types of scoring functions, AD4, Vina, and Vinado. We are dealing here right now with the Vina. If you type in /Vina, then the default is Vina algorithm. And if you want to specify AD4, then you have to specify the scoring function, which is called in the command line. Okay. And these are the centers as I've shown, and these maps are particular for AutoDock 4, not for AutoDock Vina. So these are the affinity maps for AutoDock 4.2, which uses the scoring function AD4. Okay, and this is the out argument, and these are all different types of options. You can assign different types of hydrogen bonds, weights, and the rotation arguments, everything. I think these are default in case of Vina, so you don't have to worry about that. So if you are interested in all these arguments, you can try how to do this and what observations that you are getting if you input all these different parameters. Remember one thing, that only those commands which do not have any force fields written can be applied to Vina, but where the force fields are written, those can be applied only for those particular scoring functions. Okay, so suppose this is 84, that means it applies to 84 AutoDock 4.2, and this is for Vinado. Okay, and you can apply if you are using those scoring functions, then you can apply these particular options. Okay, this is CPU argument. This is for the batch processing. Okay, and this is the exhaustiveness. As I have told before, that default is 8, and number of modes, yeah, the default is 9, but you can change it to 100 as well. Okay, and spacing argument, and this is the verbosity. So when you have the default verbosity argument, there you get only the only these modes and affinity and RMSD UV. So let's try with other one. So if you have verbosity, suppose let's say you have 2, okay, and you can define the scoring function as scoring. I think the command is scoring, and you type in Vina. Although it is difficult, but it is good to apply this particular scoring function. Okay, now you enter, and you will see how it gets executed. So yeah, now we have changed the verbosity to 2, and let's see how much time it takes. I think it will take 30 seconds or 40 seconds. Remember, I'm using AutoDock Vina 1.2.2, so you can use the same GitHub directory and configure your Vina executable based on Windows, Mac, or Linux. Let's see how much time it takes. I think it is taking a little bit time because we have changed the verbosity to 2. That means it can write different parameters apart from the binding energies. So now you can see that you have again the same the modes, affinity, RMSD upper bound, but when you go up, you will see the detailed version of the output. So the first, this is from the term called verbosity. That means it can write different types of parameters, such as the free energy of binding is minus 7.115, okay, and intermolecular energy, ligand receptor energy, flexible side chains. If you have flexible side chains, then you can get those energies in kilocalories per mole, total internal energy, and torsional free energy, unbound system. I'm not going to explain you detailed overview of the parameters that are used, because these are from the algorithms that Vina uses, and these are the energies associated with the AutoDock Vina algorithm. So this is how you get different types of energies and different types of scoring. So one bad thing over here, that in the previous version of AutoDock Vina, so when you open the folder, you will, in the blind docking, you will see only the output file, that is 6lu7_drug.pdbqt, but there are no log files written over here. So it is always recommended, if you want the log files, otherwise you have to copy this and paste it somewhere and save it, and again you run for another one and you save in that particular file, so you have to repeat it. So rather than that, I would recommend, if you use the command line, okay, let me clear this, and if you use this command line, then you just type in this greater than symbol, and then just save it as log.txt. So if you run this, it will not show the process, how the Vina executable works, but rather it writes to the log file. So if you open the log file, you can see the same output that we are getting in the command line, you are getting it here. So it will be a continuous one. So if you can see, now you can see. So the command for this one is tail -f log.txt. So this is how it performs. It is written to the log file, okay. And you can see it is being written. So see, and if you go to the file, I think everything is written over here, so you don't have to worry about copying from a command line and pasting to some other text file. So you get it from this particular log file. So this is how you perform the blind docking using AutoDock Vina. Okay, so another thing that I want to just show, that if you increase the exhaustiveness to, let's say, 32, you will see how much time it takes and how the algorithm improves and how the scoring functions improve. So when you when you increase the exhaustiveness to 32, it will take some time. I mean, it takes more time in comparison to exhaustiveness 8. So it is recommended for Vina that you use large number of exhaustiveness points, so that you get better performance and better results and better binding poses in comparison to exhaustiveness 8. Okay, so this is how I'm not going to show how it works, but you can try by your own, and you can use this blind docking approach by using AutoDock Vina. So thank you very much. Hello everyone, welcome back to my channel. So today I'm going to show you how to do the targeted molecular docking. Yesterday I have shown you how to do the blind docking, and the blind docking results are listed over here with the logged .txt file, how to generate the log file, and today I'm going to show you how to do the targeted docking. So I've created a folder called targeted docking, and in here we have the receptor file, we have the ligand file or the drug molecule, we have the conf file, the Vina executable, and also today I'm going to show you how to use Vina underscore split. Okay, so let's get to the grid parameters that I have saved for targeted docking. So this is the conf file, so you have to modify the conf file accordingly with the centers 27 minus 27 0.462 here. This is 6.409 and this one is 61.682, and the size of X is 40, and this is again 40. Remember the spacing, that is we have used 0.583 in this case, and this is the configuration file, and the command line argument for doing the targeted docking is exactly the same with the blind docking. You go to the command line, and let me increase the size. Okay, and yesterday we have shown different type of command line arguments for blind docking. The same can be applied for the targeted docking as well, just the configuration file has been changed and the spacing is same. Spacing angstrom is 0.583 over here, number of modes is 20, everything is same, and exhaustiveness, as I mentioned before, you can vary from 8 until 64. So here I am using 32 for this particular targeted docking to get more search space and better binding poses. So let's press enter and it will start. Okay, so exhaustiveness 32 will take some time in comparison to exhaustiveness 8. So while it is running, I'm going to show you how to use Vina underscore split this particular executable file. So we go to the blind docking, and the output file that is saved from the blind docking is this particular file. So if you open with any text editor, you can see different types of poses. See, this is the model one. This is the best pose with binding energy minus 6.258 kilocalories per mole. This is the inter plus intra energy, and intra energy, and this is the unbound energy in kilocalories per mole. Okay, there are 11 active torsion with different atoms, and this is the pose basically. So this is model 1 and this is again model 2. Okay, like this you have a total of 20 models. Since you have given a number of modes 20, so you get 20 different types of modes, and these are the results. So how to analyze by using different types of softwares, visualization software, that we are going to see now. Now go to the command line again. Let me minimize this. Okay, increase the size. So the command to split different number of modes or different binding poses is Vina underscore split. So you go by typing /Vina underscore split, then the option is -- input and your file name 6lu7 drug.pdb-qt. So once you enter, you will see that different types of poses starting from a 1 to 20 has been generated. So in this way you can use Vina underscore split to get different binding poses, and if you click on one of the binding poses. So you will see that it contains only one pose, that is this is the model 1, which is the first pose, and only one model can be found on each different poses. So it just separates the whole saved output, the whole number of modes into different types of modes. Since we have input number of modes 20, you get 20 different types of poses. In the same way for the targeted also, you do the same. I think the results still ongoing. Let's see. Yeah, it's going to finish. And also one more thing, that if you go to _Vina split -- help, let's see. Yeah, you have the input argument. Let me minimize this. You have the input argument, input to split the PDBQT file. In this case, this is 6LU7, the output file from the Vina run. Optional, you can give for ligand or the chemical compounds, and flexible side chains also. So basically the command for Vina _split is -- input and your output file. Okay, so the same we can do for the targeted docking. I think it is done. Let me see. Yeah, now you have the output. Okay, so you go same here, and Vina _split input 6LU7. Now you have the 20 different types of poses, and you can visualize these drug molecules, the number of modes of the binding poses using different visualization software. One of the best software to visualize PDBQT files are UCSF Chimera X and the Discovery Studio Visualizer. So if you click on any of the poses that is generated, so you see you will get the PDBQT file visualization using Chimera X, not by UCSF Chimera. So if you try to open using UCSF Chimera only, you cannot open PDBQT file because there are no extensions to open the PDBQT file. So only you can open by using Chimera X. So if you go to the the final output that was generated from Vina docking, if you click this, you will see that there are 20 different types of poses here. Now you can see there are 20 different types of poses, and if you expand this, and you have 1.1 to 1.20, you can select. This video tutorial regarding how to visualize and how to show the interaction with the protein molecule, that we see in the next video. But for now, only the PDBQT files are going to open in Chimera X and Discovery Studio Visualizer, but not in UCSF Chimera. So yeah, that's it for the targeted docking. This is how you do different types of docking algorithms, like blind docking, targeted docking, by using Vina. And Vina _split can split the number of modes into different binding poses. And one more thing, that when you see the file names, those are named as ligand 01, ligand 02. That means these are the different poses. Okay. So that's it for today, and thank you very much.